In this video, we're going to be looking at alternating series. And so as you can see from the definition, an alternating series is going to be the type of series that has terms that alternate in sign, like plus, minus, plus, minus, plus, minus, plus, minus. And we've already seen a couple of these so far. I think specifically it's going to be like in a geometric setting with a negative ratio. So if you look at 18 minus 12 plus 8 minus 16 thirds plus 32 ninths and so on, you notice it's geometric. And you see that each time we're multiplying by 2/3. I guess negative 2/3 because the sign's alternating. And if we take the absolute value of that ratio, and that's less than 1, and that leads us to believe that this series converges. Okay. And since it converges, we've actually got a formula to find the total, and it's first term times 1 over 1 minus the ratio, so 1 minus negative 2/3, that would be 1 plus 2/3. But the actual value it converges to is not nearly as important right now, especially for our discussion, is the fact that it's alternating, okay? And the fact that that negative ratio caused the alternating. All right, and so if we look over here and try to write it in summation notation, I could write it, first term 18, ratio negative 2/3. It's going to be something like 18 times negative 2/3 to the n. Your job is to kind of figure out what value of n are you going to start at. And that'll be n equals 0. Okay, but kind of what I want to point out to you here is that negative 2/3 to the n. I'm just going to remind you of this exponent property. If I take, a product to a power, that's, I can distribute the power over a product in a way that I cannot over a sum or a difference. Okay, but what I'm going to do is I'm going to look at that negative 2/3 as a negative 1 times 2/3. And then I'm going to hold that off to the side and say, all right, 18 times 2/3 to the n, that's the actual number in the geometric series that you can see. And that negative 1 to the n, that's really what's causing it to alternate. All right, now in this class, the things that are going to cause a series to alternate are going to be that negative 1 to the n, which I just showed you, and also cosine of pi times n. And I feel like that was a little less obvious why that is alternating, so I'll just, give you a couple of values of that and show you what's going on. All right, when n equals 0, I'm taking the cosine of pi times 0. Okay, so that's cosine of 0, that's going to be 1. When n equals 1, I'm going to take the cosine of pi times 1. Okay, cosine of pi, that's negative 1. When n equals 2, I'm all the way back to 2 pi, and then I'm back to where I started with 1, and then n equals 3. Okay, it gives me cosine of 3 pi. 3 pi is pretty much exactly like 1 pi, just different amounts of rotation. That's going to be negative 1, n equals 4. I'm back to 0 and 2 pi, 4 pi, that's the same spot, the cosine's 1. Alright, so for example, we've got this function f which is defined by a power series. It's the sum from 1 to infinity of cosine of nx divided by the square root of n. And it's going to ask us to write the terms of f of 0 and write the terms of f of pi. Alright, so I'll start with f of 0. So when I plug in 0 for x, I've got the cosine of n times 0, which is always going to be the cosine of 0. Okay, and on the bottom I've got the square root of n. And cosine of 0, that's 1, so I could write that as the sum from 1 to infinity of 1 over the square root of n. And if I wanted to actually write out the terms, okay, I'd start off with n equals 1, 1 over the square root of 1, that's 1, and plus 1 over the square root of 2, plus 1 over the square root of 3, and I think I get the picture from there. Okay, and if I wanted to write out the terms of f of pi, I'd say, all right, well, f of pi, I'm going to plug in pi for x, and so that'd be cosine of pi n in the numerator of that series, and that's going to cause us to have an alternating series, like I was just saying. So I start with n equals 1 if I want to write out the terms. Cosine of 1 pi is negative, so I'm going to have negative 1 over the square root of 1, plus, when n is 2, cosine of 2 pi is positive 1, square root of 2. Okay, and we know it's going to alternate, so I don't think we really need to worry about the numerator. Minus 1 over the square root of 3, and, you get the picture. And so on. Put a plus dot, dot, dot. And so we're going to come back to this example in a few minutes, but for now, that's all we're going to need for this function. I think what we're supposed to notice is that, f of 0 is not an alternating series, but f of pi is an alternating series. All right, for now I want to switch up a little bit and talk about the alternating harmonic series. So, actually, consider the sum 1 minus a half plus a third minus a fourth plus a fifth minus a sixth, and so on. So this is the alternating version of the harmonic series, which we learned last time diverges. Now we're going to see here that the alternating harmonic series does not diverge. Okay, so we're going to compute a few of the partial sums. And remember, those partial sums are just, we're going to add up a finite number of terms of this infinite series. So S1 is I just add up the first term. Okay, well, that's going to be 1. Okay, and if I add the first two terms together, that'll give me S2, the second partial sum, 1 minus a half. I can do that. Arithmetic, that's going to be 0.5. And then I can add 1/3 to that to get S3. I'd be adding 0.333. After that, subtracting 250, maybe you've got that, but that's where I might make an error. So I'm going to bring in some technology. Okay, so I've got a Desmos window up, and I've kind of defined this function f of x to being the sum from 1 to x. Just like how far are we adding these finite sums. And I put in the first 4, like we did, or no, I guess we did 3. So there's 4, 5, and 6, and if you wanted to pause and fill out the rest of your table, that's something you could do. But I'm going to keep it going, right? Because, hopefully you're kind of seeing a pattern going and seeing what's going on, that we're adding and subtracting, but adding and subtracting lesser amounts each time. And so if I keep going on, I should be getting closer and closer to one number, and I can definitely see, I think I'm going to speed this up. If I start adding a whole bunch more points, okay, I'm really getting closer to one finite value. So this sum is converging because I can see that the limit of the partial sums exists. Now, okay, I think, okay, that's off your screen. You can't even see what's going on at, 80 terms. So what I'm going to do is I'm just going to go in here and graph something else. I'm going to graph y equals the natural log of 2, and then it's going to plot that blue line, which happens to fit in just right. And you can see numerically that's very close to the values that we're getting when we add, say, like 80 terms to our partial sum. Okay, but I'll have more to say about that in a few minutes. Okay, now what we just saw there, that's the picture of converging alternating series. Really, it's the picture of the alternating series test. So the theorem is if we've got an alternating sequence whose terms are decreasing in magnitude to 0, then the corresponding series converges. Okay, so really what this is going to mean to you is if we've got an alternating series and it's growing faster in the bottom, in the denominator of the fraction than it is in the numerator, at least on the terms, then it's going to converge. And then AP Calculus-wise, with the wording that you see them use pretty frequently in the scoring guidelines for this type of problem, we have to use the alternating series test, is that the series is alternating with terms that decrease in magnitude to 0. So if you want to just when you're running the alternating series test, just give me that exact wording, you're welcome to do that. You'll see that's not exactly what I'm going to do. I'm just going to kind of hit each of the things in the 3-step process, check each of them. I'm going to be a little bit more detailed. But this statement should always work if you're trying to justify your answer for an alternating series in at least in AP Calculus. Okay, now going back to the earlier example with the f of x equaling cosine of nx divided by the square root of n. Asking, does f converge when x equals 0, and does f converge when x equals pi? Well, what we're going to do for f of 0 is we're going to copy our result from earlier. We found that was the sum from 1 to infinity of 1 over the square root of n. We look at that. That's a p series. Square root of n, that's the 1/2 power. So I'm going to say that this thing diverges. My reason to be p series test, p is 1/2, which is less than 1. Okay, and then as far as converges or diverges when x equals pi, well, we're just going to plug in pi and get what we got last time, sum from 1 to infinity of cosine of pi n over the square root of n. And this is an alternating series, so we need to run our new alternating series test. So the first question you ask yourself, is it alternating? Yes, it's got that cosine of pi n in there. Okay, are the terms decreasing in magnitude? Well, I'll just take the magnitude of the terms, take the absolute value of the terms. It's just going to lose the negative part, so it's 1 over the square root of n. And yes, that's definitely decreasing because the bigger n gets, the smaller, or the bigger the denominator gets, the smaller the fraction gets. And is the limit of the terms equal to 0? Okay, well, if I think about this, cosine of pi n is either 1 or -1, and square root of n is growing, so this limit is going to equal 0. Okay, and so if I've got all of these 3 conditions met, I can conclude that that series converges. Now, what we can't do is we're not going to be able to show that a series diverges using the alternating series test. If you go back and look at the theorem, it doesn't say really anything about if this, then the series diverges. It only says that it gives you convergence. Okay, so I know I've used a multiple choice question before. I'm not sure if I'm going to use it this year. But one of the answer choices was diverges by the alternating series test, and that's one that is not true because that's just not a thing that happens. It's kind of like converges by the nth term test. That's not possible either, right? The nth term test is a test for divergence. And the alternating series test is a test for convergence of an alternating series. Okay, so that's the alternating series test, and that's where I'm going to leave it off for this video, because in the next videos we've got a bunch of other good stuff. We've got absolute and conditional convergence, the alternating series error bounds. That's going to be all for this one. Thanks for watching.